Section 9.4, this will be our last section in Chapter 9, and we're going to take a look at something called Permutations and Combinations. The first thing we're going to look at in relation to this is an idea that you may or may not have seen before, and they're called factorials. So a factorial looks like an exclamation point, okay? So when you see a factorial notation, the value in front of it will always be a whole number, all right? So it has to be 0, 1, 2, 3. It's not going to be a fraction or a decimal or anything like that. It's not going to be negative. It's going to be a whole number. And the definition of n factorial means you take that value n and you multiply it by one less than that number, and then one less than that number. And you keep going all the way down until you multiply it by 1. So it's this series of like decreasing multiplication factors till we get to 1. And definitionally, we need to know what 0 factorial is, and you'll see why when we work some of these particular problems out. But 0 factorial is defined to be the number 1. And again, with context, you'll understand why it should be. Like it's got a really good reason for being that. So working with factorials is not very difficult, but it can be lengthy depending on how big the factorials are. We're going to start with one that's quite small, 4 factorial. So by definition, this means I multiply 4 times 3 times 1, okay? And the bigger the values are, the more likely you are to need your calculator. You might want to do this one in your head, but feel free to grab a calculator if you wish. What is 4 times 3 times 2 times 1? It's 24. Yeah. Okay, so we're going to need that for some of our applications in this section, this idea of factorials. There's several different types of counting strategies we're going to look at, and the first one is called the fundamental principle of counting. And if you've taken number theory, this shows up in number theory. If you haven't, it's not a big deal, but this is in Chapter 2 of your textbook. And it talks about how you can count ways events can happen. So if you have an event M that can occur in little m ways, and an event capital N that can occur in little n ways, then event M followed by event N can occur in M times N ways. And it always sounds funny even when I read it. It sounds like I just told you lots of letters everywhere. But the process of using this is very, very easy. It's even easier than the factorials we did on the page before. So if you wake up in the morning and you have 5 different shirts that are clean, and you have 3 different pairs of pants that are clean, and the number of different combinations of outfits you can create is 5 times 3. You choose a shirt, you choose a pair of pants, 5 times 3 gives you the number of different things that you could wear from your closet that are clean. Okay, that's it. That's how this works. But it works for more than just choosing 2 things. Maybe you're not just choosing your shirt and your pants, you're also choosing a pair of shoes, or you're choosing some amount of jewelry. We do the same thing for multiple different steps, and we would just multiply the number of options in each category. So we're going to take an example from Pizza Planet. Pizza Planet offers 3 kinds of salad, 15 kinds of pizza, and 4 desserts. How many different meals consist of 1 salad, 1 pizza, and 1 dessert? And the way I always think of it is that there's these 3 categories that you're picking from, and you're going to figure out how many options you have in each category, and then you're going to multiply them. So, how many different salad options do you have? 3. Pizza options, 15, and dessert options, 4. And then you multiply. 3 times 15 times 4. And how many different types of meals could you have created? 180. There are 180 different meals that you can make. Okay? And you can just imagine if you throw in here, like the drink that you pick, right? Or maybe if you're allowed to have 1 pizza slice or 2 pizza slices. And it's been a number of years since I've seen it done, but you've probably all are sort of aware of it. But places like Sonic, which have like the drink add-ins, They advertised once upon a time however many millions of options of drinks there are. This is what they did, right? They took all the different soda and drink options. They took all the different, add-in options, and they had to figure out what happens if they add one thing in, or if they add two things in, or if they add three things in, because you can do that at Sonic, right? You can make that a very expensive drink if you want to add in lots of flavors and turn it into some suicide something. My children would probably do that if I let them. They got a one add-in max. That's what my kids have, okay? But this is how they figure this out. They just multiply these options together, okay? So this is one way of looking at counting. And these are distinctly different options, right? Like, it's not like you've got two choices from among three categories. You pick one thing in category 1, one thing in category 2, one thing in category 3. It's generally discouraged to wear 2 shirts and no pants, right? Can't do that. Now, that's because these categories are distinctly different. And we're about to change that and not look at things that are distinctly different categories, is why I mention it. So when you have distinctly different categories, fundamental principle of counting works really well. All right, another counting strategy is permutation of like objects. So let's talk about what it is, and then I'll tell you how it's used. So if you have n elements, n objects, and you're going to choose a few of them, r sub 1 of them, which are alike, r sub 2 of them are also alike, all the way up to r sub n, whatever that looks like. And alike objects are indistinguishable. Then the number of ways of choosing all these different, options is n factorial over r sub 1 factorial, r sub 2 factorial, all the way to r sub n factorial. So the example I have is a perfect example of this object. And we're going to talk about starburst. I should really bring food when I talk about this chapter. We talked about pizza now. Now we're talking about starburst. I'm getting hungry too. All right, a package of starburst. So in the package of starburst, there are several colors, unless you get the all pink one, right? There's a package of starburst now that says it's all pinks. I would sign up for that. I've got excited faces. Yes, it's an all pinks. There's also ones that just says all reds, and it's just pinks and reds, I think, and maybe it throws in a watermelon flavored one too or something like that. So this is just the traditional starburst package we're talking about here. So it's got yellow, orange, pink, and red, the 4 colors. And there's a combination of colors inside of this particular package. Well, the question has to do with how many different ways, that is distinguishably different ways, could I eat the package of starburst, right? Do I eat all the pink at the beginning? No, I save them all for the end. I might even throw away the yellow if it were me. I don't care about them, okay? But that's the deal, right? Like if I eat the pink as the first pink, it doesn't matter if it's pink 1, pink 2, pink 3, or pink, how many do I have? Pink 4 or pink 5. It doesn't matter. They all taste the same. It doesn't matter which one of those pinks I pick. It's the same flavor combination down the road, okay? So there is no way to distinguish one pink starburst from another pink starburst. Make sense? Okay. So when this is the situation where there's these objects that are indistinguishable, candies are a really good example. Another one that your book likes to use is they run colored flags up a flagpole. You have a certain number of blue flags, a certain number of red flags, something like that. Another type of thing that you see happen is that if you were talking about something within their categories, right? So like you were identifying vehicles maybe only by their make of their car. Like every car that's a certain make of the car is considered to be the same kind of car. Another option you can think about from this perspective is, like, let's say you were trying to look at the distinguishably different ways of selecting a committee, and all you cared about was whether the person's got brown hair or blonde hair, or is a boy or is a girl, right? Where you're categorizing things. So the objects don't necessarily have to be identical, but the category that you're thinking about them in would be making them indistinguishable. These objects are identical, right? The pink starburst looks just like the other pink starburst. Okay, so the way that this works is we need to figure out how many total starbursts we have. So we have 4 over here, 5, 3, and 2. How many starbursts is that? 14 starbursts. So that's the number that goes on top, 14 factorial. Okay, so our total number of objects, elements, go on top. And then in the denominator, we take each of the different things that are indistinguishable and put them in factorial notation. So the first one was a 4, so it's 4 factorial. and then 5 factorial, and then 3 factorial, and then 2 factorial. Okay, is that all right? Okay, now in reality, your calculator even has a factorial button. Like you could actually type 14 and put the little exclamation point. Many of calculators do, in fact. But as a general statement, the bigger that number gets, and we're going to see the numbers getting like maybe up to 50 in a minute, your calculator won't be able to give you a calculation for it anymore. So I want to show you how we work this in general because these numbers with factorials get big very quickly. So in general, a better idea is to write the 14 out until I get it to match something on bottom. So 14 times 13 times 12 times 11 times 10. My biggest number on bottom is a 5, so I'm going to go all the way down to 5. 10, 9, 8. Okay, I'm going to move this. Oops. One more time. 7, 6, and 5 factorial, and I'm going to stop. I could write out 5 times 4 times 3 times 2 times 1, and that's okay, and it wouldn't be the worst thing in the world, but the reality is that the 5 times 4 times 3 times 2 times 1 would be on top and on bottom. They match exactly. So I kind of can stop at the 5 factorial, and if they match exactly, not just if they divide out like the 5s, but 5, 4, 3, 2, 1 is exact matches, I can cancel them from top to bottom. I have other things here though too, so I'm going to write those out. I can only leave one of them in factorial notation. The others need to be written out. If you don't want to write out the 1, it doesn't really matter, but the others, 4 times 3 times 2, that part needs to be written out. I have 3, 2, and 1, and then I have 2 and 1. Okay, so as promised, 5 factorials cancel out completely. And here's the other thing. As we're canceling these, everything in the denominator was going to cancel. Okay, it has to. I can't have like 2.5 ways of getting something to happen, right? It's either 2 or it's 3. Right? I can't have a half number of ways when I'm counting something. So everything's going to work out to being canceling out the denominator completely so that I end up with a whole number at the end. All right, so you can pair some things together nicely. For example, maybe you decide, hey, look, there's a 3 times 2, and that works really nicely to be 6. Maybe you don't. Maybe you mark out different ones. It doesn't matter, but you're just trying to find things that mark out. When you get to the 4 times 3, hey, look, that's got one too. Look, 4 times 3, that's 12, so that cancels. I like to pair things up, but you don't have to, right? Like this 2 right here doesn't have a perfect pair. Even if I join it with the 2 over here, I don't have a 4 on top anymore. So instead, I might choose to check cancel out this 2 with the 14. I'm just marking it out with an even answer, right? And I can do the same thing with this 2. This 2 could cancel with this 8 maybe. Or maybe you decided to cancel it with the 10. Now, because I've made so many marks, it's very easy to lose factors. So be very careful at this point to go back and capture everything. Highlighters, colored markers, things like that are a good idea. I'll change colors on mine, in fact, too. So I have a 7 and a 13. 11 and 10, 9, 4, and 7. I need to make sure all of those numbers get included when I multiply. And at this point, I have no intention of doing that by hand. That would be a big number, so my calculator will be my friend. So we're going to do 7 times 13, times 11 times 10, times 9 times 4, times 7. Is that a big enough number for you? It's big, isn't it? Surprisingly so. It's actually 2,522,005. Did I get them all? Yeah, 520. There are over 2 million, about 2.5 million ways of eating that 114 package of Starburst. It's crazy. It's crazy. All right, you ready to look at the last 2 ways of counting strategies? There's 2 more. Okay, so far we have permutation of like objects, that's the one we just did. We have the fundamental principle of counting, right, where it's got these different, completely different categories, right? The starbursts weren't quite like that. They were these indistinguishable objects. The next one is called permutation of unlike objects. So in this one, every object is some way distinguishable. So the order matters when we're working with a permutation, either of like or unlike objects, but this one is distinguishably different than the next one I'm working on because the order matters. Okay? So anytime we're working with something that you think, is this a permutation or a combination, which we'll get to in a moment, you have to ask yourself, are they talking about the order? Does the order matter in this context? All right, so notationally, we have n elements, so n different objects, and we're choosing r of them. So imagine, right, we were doing our committee that went to Hawaii. We had like, I don't remember how many it was, 13 people or something like that, and we chose 3 of them to go. Right, there's 13 people and we chose 3 to go. On this one, however, the order would matter, right? On that one, it wouldn't matter if I was selected first to go on the trip to Hawaii or third. I still got to go on the trip to Hawaii. Agreed? However, if it was the trip to Hawaii and the person who was selected first got to go for 2 weeks, and the person that was selected second got to go for 1 week, and the person who was selected third got to go for 2 days, then it would matter. Okay, so it's not about the specific choosing, it's about the kind of outcome that happens after you've been chosen. So notationally, this is NPR. Again, your calculator has a button for this. We're going to do it out by hand because not all of your calculators will have a button for this. On the top, it's the n factorial. It's the number of people that we've got, or the objects that we have in the situation, okay? So in my last situation, if my starburst had been distinguishably different, it'd still be 14 factorial on top. There's 14 starburst. However, the denominator is telling you how many you don't choose. So if I choose r people to go, or r starburst to eat, then n minus r would be the number I didn't get to go, or the number I didn't get to eat. Right? So the denominator is n minus r. So let's look at an example and it'll make sense. We have a raffle. 30 people enter the raffle. The person who wins first place wins $100. The person who wins second place wins $50, and the person who wins third place wins $25. Does it matter if you're selected first, second, third, or not at all? It matters because your reward, your outcome, your prize is different, right? That's why the order matters here, is because your prizes are different. In how many ways can prizes be awarded? So the number 30 matters, and the fact that we're selecting 3 winners is what matters. So I have 30 people who are entering, enter for a chance to win, and 3 of them win. So this is 30, and I'm picking 3 people. So the 30 goes on top. It's always the total number of people or elements or objects that I've got that I'm choosing from. And then on the bottom, you can think of this in one of 2 ways. One way you can think of this is literally I'm going to subtract 30 minus 3 on bottom. I can write that down. 30 minus 3. There's nothing wrong with thinking about it from a formula perspective. You can do that. The other way of thinking about it is instead thinking about the denominator is how many people don't get chosen. Well, how many people are not going to win anything? 27 of them, right? Well, that's the same thing that I get if I did 30 minus 3. But conceptually, I'm just thinking about it more from an application perspective than a formula perspective. Total number of people on top, people who don't win on bottom, right? 27 of them. Okay, 30 factorial is too big for your calculator. Even if you've got the factorial notation, it will not let you do this. So it becomes absolutely crucial that I write it out like I did on the last problem. I'm going to write the 30 out, until I get down to 27. 30, 29, 28, 27 factorial. That matches my 27 factorial on bottom, which is lovely because it eliminates. Not because 27 divides by 27, but because 27, 26, 25, all that multiplied out is identical on top as on bottom. And all we're left doing is multiplying 30 times 29 times 28. What is 30 times 29 times 28? 24,360. That's the number of ways I could select 3 winners who are getting 3 different prizes. Okay? We're going to do one more type of problem, an example, and then we'll stop for today. The last one's combination. Combination is almost identical to permutation, except the order doesn't matter. So the problems start out sounding really similar, and you just have to ask yourself and figure out, do they care about the order? Is that part of what's being asked? You'll notice that the combination formula has the permutation formula and sort of embedded in it. It's still got the n factorial on top, and it's still got the n minus r factorial on bottom. But it has an additional r factorial on bottom. So not only am I dividing by the number of people who don't win, I'm dividing by the number of people who do win, with factorials on each of them. And the reason is because it's indistinguishably different. So in the last case, those 3 people who won, it was different if you won first, second, or third place, right? Or prize or whatever. It mattered. But in the next scenario, it doesn't. And you have to be really careful about the structure of the problem. For example, some of you might be thinking, I just said first, second, third place. Well, that sounds like you're running a race, or somebody's in a swim meet or something like that, right? So does order matters? And the answer is it depends. And here's what it depends on. Does it depend if you're in a qualifying round or if you're in the finals? Because typically speaking, think about like the Olympics. They have heats. You know what I'm talking about? If you guys watch the Olympics or something like that enough to know any competitions. They have heats. And they take maybe there's 30 people who swim, but they can't put them in a pool that's got 30 lanes in it. The pool's not that big, right? So maybe they have 3 heats. What does it mean? Well, it means that the top 2 people or the top 3 people in that heat move on. Well, if that's the case, it doesn't matter if I'm first, second, or third. If there's 3 people moving on, I still get to move on, right? It doesn't matter. But in the finals, they're going to give me a medal or not, right? And it matters because if I get first, second, or third place, my medal's different. It's not a matter of moving on. It's a matter of the final outcome. So the structure of the problem and how we're constructing it really matters as to whether or not the order matters. This question is almost identical to the last one, but what's different? They're winning the same amount. Last time it mattered whether I was drawn first, second, or third. This time, doesn't matter in the slightest, right? First, second, and third place all get the same prize. So it's indistinguishably different whether or not I'm drawn first, second, or third. So this, the order doesn't matter, is what makes it a combination. I still have 30. I'm still picking 3. But on the top, I have my 30 factorial, and on the bottom, I have my 27, right? The losers. They don't get picked. But I also have the winners because the order in which they get picked doesn't matter. That's why we divide by the 3 factorial, is because the order in which they get picked doesn't matter. So, when I'm writing this out, I still have 30 times 29 times 28 times 27 factorial, and I still stop at 27 because it matched the 27 factorial on bottom. But on bottom, I also now have a 3 times 2 times 1. So the 27 factorials cancel. But I need to divide by the 3 and the 2. You can combine them and make them a 6 if you wish, or you can leave them separate. If you combine them and make them a 6, you might decide, hey, look, I can divide the 30 at the beginning by it. That's great. Maybe you look at it piecewise and you say, hey, look, 30 divides by 3, really nice, and it gives me 10. Now, technically, yes, could you divide with 2 by 10, right, the 10 by 2? Yes. But maybe you were looking at it and said, I can divide the 28 by 2 and get 14. The actual values you divide don't make any difference. What matters is that you divide something that will work, and it will always work, whether I pick the same numbers to divide on top or as you or not. So these are the numbers that I chose, and then I'm going to multiply 10 times 29 times 14. And what is 10 times 29 times 14? 4,060. It's smaller, right? It's smaller because the order didn't matter. And so there's fewer ways for the outcome to happen. It's distinguishably different, right? Because I could win first, I could win second, or I can win third, and it doesn't make any difference on my outcome of my prize. Okay, so here's what's going to happen when we come back next time. We're going to be taking a look at examples, but they're not telling you in the example which of these strategies to use, and you have 4 strategies. Fundamental principle of counting, permutation of like objects, permutation of unlike objects, and combinations. So you have to make the decision on your own based upon the context of the problem. So that's what we're going to be working on next time.